So we have looked at the kinetic molecular theory and saw what has happened with our gas molecules. We have looked at the variables and determined what they mean and how they're interacting with each other, their relationships. We looked at that combined law. So now we're going to look at our final laws. Today, we're going to look at ideal gas law, particularly in this video, and then in your next slide set, you will watch a video on how to solve for Avogadro's law. So let's do a little refresher real quick. Kinetic molecular theory. It states that gases or particles in an ideal gas. Okay, so remember, we're living in an ideal world. Okay, they're going to have no volume. They're going to bounce off of each other and not lose energy. That's what elastic collisions mean. They're going to be in constant random straight line motion. Okay, so they don't really have a path. They're just going to keep moving and changing direction when they hit something. They're not going to be attracted or repel each other. Okay, there's nothing going to cause them to clump or stay separate. And their average kinetic energy is related directly to their temperature in Kelvin. So if your temperature in Kelvin goes up, your kinetic energy goes up. So the ideal gas law is PV equals nRT. And we have actually looked at 4 of the variables. So P being pressure, V being volume, T being temperature. We saw all of those in our combined law and the offshoots of it. We looked at N, which was the amount, our number of moles when we looked at our variables. R is a little separate. It is called a constant. And what a constant is a number that is set for us based on years of research and theory. And so that is set for us. And so we're going to look at what this R stands for. It's for a gas constant. And we're going to look at 2 ways or 2 numbers that it's looked into. So this law actually brings all of our gas properties that we kind of talked about together. So when we increase temperature, we mess with pressure, we change the volume, we see how many moles there are. All of that stuff is combined into this law. And it can be derived from experiment and from theory. So we're going to look at theoretical because we're not in class right now, but we could also do this law in an experiment, which we'll probably see later this unit. Okay, so your ideal gas equation, okay, is P times V equals nRT, okay, where P stands for pressure, V stands for volume, N is the number of moles, R is our universal gas constant, which can be written as 0.0821 atoms, liters, over moles, Kelvin, or it could be 8.314 kilopascals, liters, over moles, Kelvin. There's also another one that's listed in your chemistry reference table for torr, but we don't use that one a ton. Okay, and then finally T is for temperature. Okay, so as we increase temperature, we're changing the number of all that stuff. All of these things impact each other. Okay, so here are different things. Like I said, we have pressure, volume, temperature, moles, and then gas constant. We've kind of talked a little bit about this with standard temperature and pressure. We haven't used the initials STP, but that's what that means, standard temperature and pressure. That, again, temperature is at 0 degrees Celsius or 273 K. Pressure is at 1 atmosphere or 101.3 kPa or 760 millimeters of mercury. Our volume, our standard volume is 22.4 liters because that's the volume made up of 1 mole, and our standard is 1 mole. Okay, so let's walk through a problem together. So what is the volume that 1.9685 moles of iodine will occupy if it's in this condition? You have a temperature of 300 degrees Celsius and a pressure of 0.9737 atmosphere. So I want to write down my chart and I want to write down all my given information. Okay, so my N is the number of moles, my 1.9685. My temperature is 300 degrees Celsius. My pressure is 0.9737 atmosphere. And my constant, this is the big thing about the constant, you have to match the constant with the pressure given. So if your pressure is given in atmosphere, you're going to use the constant that has atmosphere in it. If it was given in kPa, then use the constant from kPa. Okay, if it's given in torr, you use that constant. Okay, so and we were trying to figure out V. So the next step is we're going to manipulate our formula. Okay, and to get V by itself, we divide both sides by P, and we get V equals nRT over P, and we're just going to plug those numbers in. Okay, and then solve. Okay, however, you notice I don't have an answer here, and there's a reason for that. So take a second and look at the fact that there is a mistake. Okay, when we wrote down the information, we forgot one crucial step, which is all of our gas calculations, we have to use Kelvin. And so when we did 300 degrees Celsius, we forgot to change to Kelvin, which means we forgot to add 273 and use that number. So really our temperature should be 573. Okay, so now we're going to redo the problem, switching out our 300 for 573. Okay, and I get that the volume is 95.11 liters of iodine. So that is the volume that this amount of moles will take up in with a pressure of the 0.9737 atmosphere and a temperature of 300 degrees Celsius. That's that. It's the last step. It's just like we've been doing. You are going to have your information, and then you're going to plug it in and chug along with your calculation. The last thing I want to mention is your last slide of your notebook. And this one doesn't have its own slide set because Avogadro, we kind of talked about throughout this whole thing, but Avogadro is the amount of space or volume that your moles are going to take up. And so it has its own formula, V1 over N1 equals V2 over N2. Okay. And this video in the slide will walk you through how to solve the problem that's listed in your notebook.